Good evening, everybody. Let's wait for a few minutes and then we'll start. All right, so let's get started. Can you please confirm if you can see my screen, if the Colab notebook is visible? Then we can start. Okay, so for anyone new here, my name is Buruj. I'm a PhD student at IIT Delhi. I research graph machine learning. We conduct these practice sessions every week, and the recordings are available on this YouTube channel. So if you are unavailable during the slot, you can always watch it later. We usually discuss the coding side of your courses, and any questions that we discuss, you can also find those in this GitHub repository. For example, this is from past week, week 3. We have the solutions here. Okay. So the purpose of these lectures is to get you um, to build sort of your muscle memory for doing these problems so that you can build some confidence. So you can fire up your Colab notebooks and we can start with the first question. And let me also move this to a different screen. All right. This is our first question. Okay. So you are given an e-commerce company. They claim that their average delivery time is 5 days. Okay. You want to test whether their actual delivery time is greater than this thing. So we have some sample for that. So given, if we add a few things, if you assume that their standard deviation is 2 days, can you test their this hypothesis that the mean is equal to 5 days against the alternate hypothesis, which says the mean is greater than 5 days? Okay, so you would like to do this in two ways. You would like to calculate the p-value against an alpha of 0.05, and you can also compute a critical value, or you can say a z critical, for the same thing to decide. Following this, you would like to check whether these two tests return the same results or point to the same decision, the same decision. So for this, let me give you the path. Mhm. Okay, so this is your data. It looks like this. You have your order ID like 1, 2, 3, 4, 5, and the main thing here is days. How many days does it take you? So let me paste this in the chat. Mhm. Yeah, I think that is everything for this part. Yeah. If you have any questions, let me know in the chat, or you can also unmute maybe. So it is 7:10. You can take till 7:20, and then we'll go ahead. Tanu says I'm not audible. Can the rest of you confirm if you can hear me?
Yes, sir, yes, sir.
Yeah, so the laptop is right in front of me. I don't think I can increase the volume anymore. Okay, I'll try. Maybe I'll speak louder. So to reiterate the question, an e-commerce company says that their average delivery time is 5 days. You have a hunch that it is more than 5 days. So you want to test their claim. That is, if I take a sample of, let's say, this many average deliveries, is the average delivery more than that? And can I trust that particular value? Is there any statistical significance to that? So to do that, because you know the population um, variation, the sigma for the whole population is 2 days, you can apply a z-test. And for a z-test, you can go in either way. You can calculate the p-value, or you can calculate the z-critical. And you have to decide whether to go for a one-sided or a two-sided thing. I mean, it's already given that's a one-sided z-test, but yeah. The full thing does 200 rows. Can we have a raise of hand for people who have done it? If enough people are done, we can start early. All right, so let's start with the solution. Let us first jot down the information that we have. We know that from the entire population, we have taken out a sample. This is our sample shipping data, and we know the sample size as the length of this data. We also know that the hypothesized mean is 5 days, so we can note that down. It is preferable to write it as 5.0 rather than 5 because it helps Python. Because sometimes what happens is you have a float and an integer, then it will convert one data type into another. It is best to stay within one. So you have a hypothesized mean of 5, and afterwards you know that your alpha that you want to compare against is 5% or 0.05. You also know that your population standard deviation or your population sigma is 2 days. Maybe we can write it with this. Yeah. From this, we can compute the standard error, and we also know the sample mean. The sample mean would be the mean of this thing. So we can write shipping data delivery days dot mean. So this is a sample mean. For the standard error, the formula is that you take your population sigma because that is known and you divide it by the square root of your sample size. Okay, so this is the basic information that we will work with. So now we would like to do it in two ways. First would be the p-value approach. So to use the p-value, what do we need? The first thing is, given the alpha, we would like to know the z-stat, which we already have, and then we would like to calculate the p-value using stats dot norm, or we can in fact say scipy dot stats dot norm dot ppt, or in fact in this case just the cdf. So the cdf is essentially your if you're familiar with the probability terms like the pdf and the cdf, the cumulative distributive function, you can do scipy stats norm, and here you will find the CDF. So this gives you the cumulative distributive function. So you want to find out for this particular Z stat, what is the probability that falls under this. So how do we do this? We already have the alpha, we compute the Z stat. The Z stat is given by my sample mean subtracted by the hypothesized mean. Okay. So we shift the mean and then we normalize by the standard error. Okay, so this is our z star. This is the point on our standard normal curve. And now we would like to find what is the area under the normal curve on the right side of it. Now, why do we want to do it on the right side of it? Because the hypothesized mean was 5, and we are saying it is more than that. The alternate says it is more than that. If it were, the alternate were to be less than that, then we would take the area on the left hand side. Either way, it is symmetric, but still. So when we have this to calculate the p-value, we would say stats dot normal, so it's essentially the normal distribution, give me the CDF value on the Z star. So this would give me the area on the left side of the curve. Since I want it on the right side of the curve, we subtract this part from 1. So this gives us the p-value. We can also print this. We can say our p-value is equal to this much. Now, how do we decide what how do we decide between the null hypothesis and the alternate hypothesis? We have to compare the p-value against the alpha. So we can say if the p-value is less than alpha, then your decision or your p decision in this case would be to reject the null hypothesis. Otherwise, your decision would be to fail to reject the null hypothesis. Notice we don't say that we accept the alternate hypothesis. We just say that we don't have enough evidence to reject the null hypothesis. So if we run this, That's something. Yeah. So if we also print the alpha with this, so our alpha was 0.05, but our p-value is greater than that. Therefore, we fail to reject the null hypothesis. Now, if we would like to do the same thing using the critical value approach, how would we do that? In that case, we would need the z critical. How do you get that? Again, we go to the standard normal distribution. And in this case, we have to do the reverse thing. That is, we already have the alpha value, which is essentially the value on the curve under which I want the x-axis value. So this is given by the function ppf. As usual, you can refer to the documentation. The ppf is the percent point function. It is the inverse of the cdf, as I said. The cdf gives you the probability. This gives you the inverse. That is, at what point will you receive this much probability? So you have the ppf, and what do you pass in? You pass in 1 minus alpha rather than alpha. Alpha would give you the left hand side, 1 minus alpha gives you the right hand side of the curve. So you have z critical, and how do you decide? You already have the z stat. If you would like, you can recompute it. And to make a decision, you can say if my z stat is greater than my z critical, then essentially this thing happens. You can call it decision z, decision z, and we print decision z. Again, we fail to reject it, and we can also print these values for our own sake. We can say z statistic is this much, and our z critical is this much. You would notice that our z critical is on the left side of my z critical. Therefore, we fail to reject the null hypothesis. So in either case, we receive the same output. So for the moment, yes, for the moment, we cannot reject the claim by the company that the average delivery time is 5 days. Any questions about this part? Okay, in that case, we can go to the second question. Since we know how to do this, the second one should be easy. In the second case, we have a restaurant manager that believes that the average tip at his restaurant has changed from the historical value. Historically, from his calculations, he knows that people on average give a 15% of tip. He believes that this value has changed. It can either be a bigger value or it can be a smaller value. So, as usual, you know that the historical variance or the historical sigma, which in our case is the population sigma, you already know you're given that it is 5%. Against an alpha of 0.05, which is essentially 5%, can you conduct an experiment to either accept or to either reject or fail to reject the hypothesis that this thing happens? So your null hypothesis in this case would be that the mean is still 15%, and your alternate hypothesis that it is different. How do you write it? It is different than 15%. So you can do the same thing. You would like to make this claim using three approaches. The p-value, the z critical, and the confidence interval. So it's almost 7:30. You can take 10 minutes. It should be easy, given that we have done this much. So Tanu and Siddharth, you're asking the question about this one, um, the second one or the first one? Okay. So the critical value essentially tells you the same thing. So when you go for the z test, for example, you are essentially playing with a standard normal curve. Okay. So you have something like this. So suppose I tell you that um, we have this particular hypothesis, for example, this null hypothesis of 5 days, the alternate hypothesis is greater than 5 days. So normally, if I were to plot this particular Gaussian distribution by sampling from this, the mean would be at 5, and we will have some standard distribution. But to transform this into a normal distribution, we first have to change the data so that the mean now lies at 0 and the standard deviation is slightly different. So essentially, that is how you convert your x values into your z scores. Okay. So once you have these z scores, all of them are transported to the same curve because every curve is now a standard normal curve, mean 0 and standard deviation like this. So if I give you that z score, that is, suppose I tell you your z score is 0.35, you know that I am at 0, I have to go to 0.35. Now I am at this point. If I ask you the probability for this particular z score, you have to calculate the area on the left side of this thing. Okay. So the main, good part about this is that give any data set, if you change it to the z score, all of them essentially land into the same distribution. You don't have to do different distributions. There are even tables for the z score. That is, if your z score is 0.7, you know the area on the left side. People have tabulated that part. So in our particular case, let's say when we want to do the critical value part, we say that if I know this particular z score, that is, I'm assuming that my null hypothesis is correct. That is, it is actually 5 days, but my sample mean is quite far. Okay. My The original mean is here, but my sample mean is here. What are the odds that this can actually happen in real life? That is, the mean can still be at this place, and with a good chance, this will land here. Okay, so how would you compute that essentially? So you would like to find out that for my sample mean, let me first change it into my z score. So that becomes your z stat. Here, you have changed your sample mean into your z-score. So now you have landed on this particular graph. Now you would like to compute what is the area on the right side of it. That is, this is my chance of falling into this part. So if you were to compute this thing, um, essentially the alpha is some other thing. If you were to compute, let's say, the CDF thing, it gives you the area on the left side of this graph, this side, but you want the area on the right side of the graph, so you take 1 minus that value. Okay, so in this case you already have this z score. On the other side, you want to find out what is the point. If I am on the left side of that, I'm good, I am on the left side of it. But if I am on the right side of it, that's a problem. So you want to identify that particular z point. You know your z point, but you want to find out the z point that distinguishes the acceptance part and the rejection part. That becomes your z critical. Okay, and that z critical you find out using this alpha value. Okay, this alpha value says that the area on the right side is this much. Find out the point that gives you this particular area. So this is the inverse of your CDF. This gives you that z critical. If you are on the left side of z critical, then you are in distribution. That is, you cannot reject the null hypothesis. If you are on the right side of the z of this particular z critical, then you have to reject. I mean, yeah, then in that case you can reject the null hypothesis. So it is a bit difficult without drawing this on board. So I hope this is clear. If it's not, maybe I can share a video or something with you. I think a plot would actually be good in this case. Let me see if I can find it. So Tanu and Siddharth, I hope it helps a bit. Maybe when I upload this notebook, I'll add a few plots so that you understand that is those particular lines, the area that I'm talking about. Is the recording available? Yes, the recording is available. Yeah, so if the screen is visible, maybe you can revisit this part. Siddharth and Tanu, you notice this graph. If you have this alpha, then this particular line becomes your z critical. And if your z stat is on the left side of z critical, then you cannot reject it. If you are on the right side, then you will reject it. That's the crux of it. Okay, so let's start this one. This is pretty much the same thing. The only difference is that last time we knew that we only want to compute it on the right side. This time, the alternate hypothesis is an inequality. Sort of like mean is not equal to 15. It could be greater, it could be less. So we would go for a two-sided z-test. All right. So let us note down the things that we already know. We know that our alpha is essentially 0.05 or 5%. We also know that the hypothesized mean is 15%. We, since we are working with percentages, maybe we can leave it at 15%. Our population sigma is given that it is 5%. So we can again leave it at 5%. And since our tip data set does not have a percentage column, let us create a percentage column. We can say tips tips percentage is equal to tip divided by the this is the tip, this is the total bill. So we have total bill. You divide and you multiply it by 100 to create a percentage. Okay, so this is the information that we already have. Now we have to go for three approaches. We have a p-value approach, we have a z-critical approach, and we have a confidence interval approach. Okay, so let us do this again. So for the p-value, what do we essentially want to compute? We already know that our alpha is 0.05. So this alpha is essentially a probability. That is, with this much probability, the chances are that even though your tip percentage is 15%, you still might get a very weird outcome. Okay, so we want to say that is our probability less than this particular probability? That is a very unlikely outcome. That is, without changing the hypotheses, you can still manage to get this data. So to get this, we first would need that z value on that curve that a particular sample is providing us. So we have to compute the z stat. So for the z stat, what do we need? We essentially need a sample mean from which we will subtract the hypothesized mean, and we will divide this by the standard error. We have this term, but we haven't calculated these two terms. So if we have to compute these, we have the sample mean as tips tips underscore percentage dot mean. This is our sample mean. Then we have the hypothesized mean. We already have this. Then we have to calculate the standard error. So our standard error would be the population sigma divided by the square root of our sample size. We should maybe also write sample size here. Okay, so this gives us the z stat. For this particular z stat, what is the probability on the right hand side and similarly on the left hand side of it, because this is a symmetric thing. So for this case, we have our p-value. It would be, we compute it as we did before. We say 1 minus the stats.norm.cdf for the this particular z stat. Since this is a two-sided thing, it is a good practice that you take the absolute value of your z stat, because your z stat can be negative. If you are doing a one-sided test, then you don't keep, I mean, alter the sign, because the sign matters whether you're taking the one-sided on the left side or one-sided on the right side. In a two-sided case, because you are anyway going to take both sides, so it is best to take the absolute value, or essentially the positive value. So once you have this, this is the probability on one side. You have to double it, because the normal distribution is symmetric. You can just double it to get the value, to sum up the value on both sides, and this becomes your p-value. Based on this, you can essentially print out what we printed out first. That is, if my, we can even do this thing, whole thing. That is, my p-value was 0.0, my alpha was 0.05, and my p-value is actually pretty low compared to my alpha, so I can safely reject my null hypothesis. So this was one way to do it. Now, if we are to do it using the critical method, what do we need? We need to compute the z critical. But if we look at this again, two-sided z-test. This time we are looking for something like this. You notice that these two blue lines, these are your two critical values. You need one critical value on the right hand side and one critical value on the left hand side. The alpha that we just computed is this red area on the right hand side and the red area on the left hand side. So we have two critical values this time. So we will have z critical lower, it would be something, z critical upper, this will also be something. So how do we compute that? For the lower side, it is simply your stats.norm.ppf. As I said, ppf is just the inverse of cdf. You already have the area, you want the value that gives you that area. So on this side, you will use alpha divided by 2. So why are we dividing it by 2? Because we have to distribute it on two sides. You see, half on this side, half on this side. So we have alpha divided by 2. This is our z critical lower. For the z critical on the upper side, we take 1 minus alpha divided by 2. So we have the z critical lower, z critical upper, and we already have our z stat that we computed earlier. So how do we decide whether to accept, whether to reject or fail to reject a null hypothesis? We can say if my z critical, or maybe if my z stat is less than z critical, or my z stat is greater than my z critical upper, in that case, I will reject it. I can write decision underscore z is equal to, we can again copy this part. We can say reject or we can say fail to reject. If we print this again, print decision z. So in both cases, we have rejected. Maybe we should also print this. That is, what are our z scores? We can say print my z statistic was this much. We named it something else this time. So we have z stat, we have our z critical. This is in this case a set on the left hand side, on the right hand side. We can say z critical lower, z critical upper, and then we can see what we get. And maybe we can also add a decorative line. Okay, so these are the results based on our p-value. These are the results based on our z critical thing. In either case, we see that the z statistic is outside this particular window. That is, it is greater than this side. And in this case, the p-value is much less compared to the alpha. So in either case, we have rejected the null hypothesis. Coming to the final one, that is the confidence interval. If we see z-test confidence interval, in this case, is there a good graph here? Yeah, so it looks something like this. In a confidence interval, you essentially have to find two bounds like the z critical values. And if you are inside this particular band, then you cannot reject the null hypothesis. This is the crux of it. So how do we compute these two bounds for the z critical thing? We have to compute the confidence interval margin. It is given by your, I mean, in this case, you would have to know, I mean, at what confidence you want to, I mean, identify it. Suppose we say 95% confidence. So this essentially means the same thing because your alpha is 5%. So just the Z critical would work. If you had some other percentage like 80%, 60%, then this would value would accordingly change. So if you have this 95% confidence, this matches our already alpha computation. So we can just say that I have my Z critical upper, just multiply it by the standard error. This gives you your CI margin. And now you will have your CI lower and your CI upper, just like you had your CI, your Z critical lower and your Z critical upper. So this would be your sample mean minus CI margin. Notice this. This is your mean. This particular value is your CI lower. And you have sample mean plus your CI margin. And how do you decide? You do something like this. You say, if my sample mean is less than, or maybe we can do greater than first, greater than CI lower, or in fact, yeah, or in fact, would be better, or the sample mean is should be less, and this should be greater than CI upper. In that case, I will do this. All right. So again, we rejected. Oh, wait, I think we did not print it. This would be decision CI. What did we change? I think this is wrong. Yeah, no, that's right. So if your sample mean falls within the confidence interval band of your original population distribution, then you can either reject it or you can fail to reject it. We could write a similar thing for this whole thing. We write confidence interval. We don't need this. We have our CI lower, CI upper, CI lower, CI upper, and we can print a blank line here. Yeah, but in this case, we can write sample mean. Yeah, yeah. So this falls outside this band. Yes. So we have question one, question two. Moving on to question three. Any questions in this part? This is pretty much the same thing, just doing it on both sides. Okay, if we have no questions, we can move to the t-test. up to now, in both of our questions, we knew the original population's variance. Suppose you have a population where you don't know the variance and you just have a sample. In that case, you cannot compute a z-test. You have to go for a t-test. So you have a scenario where we can write this in a different line. A school claims that the average math score is 70 for its students. You want to test whether this claim is true or false, but you don't know the population standard deviation. So therefore, the z-test is out. You have to compute the t-test. So can you compute the t-test for this particular case? Let me give you the path. So you will notice that we are only concerned with this math score. So you have to do it in two parts. Manually calculate the t-score. You can say manually conduct the t-test, and then we will use the library. Use a library to conduct the t-test. Okay. Again, you can refer to your lectures. This should be pretty simple. It is almost identical to what you've done in these two. As usual, you can use an alpha of 0.05. That's pretty much standard. If anyone was able to do it, you can try an additional problem. Rather than taking the entire sample, these 1000 rows as a sample out 50, 100, or 200 points as your sample and see how your t-test score varies and see how your decision varies. Essentially, you are noticing the effect of your sample size on your t-test. That is, can you even trust it at small test sizes? Proportion means number of samples in favor. We are not speaking about proportions at the moment. This is the average score. Question number two. Pranay, are you speaking about the second question? So in the second question, it says a manager believes that the average tip has changed. So the average tip essentially means the mean of the tips that you receive. There is no proportion here. Suppose I did not give you this particular total bill column. I just give you the tip, that the percentage tip you receive. Like sometimes you receive 10%, sometimes you receive 20%. The manager says that we used to get 15%, but now we are getting more than that. In the proof of standard deviation. Standard deviation. So the sample standard deviation or the population standard deviation. So the population standard deviation is given, and the standard error for the sample is also pretty simple to compute. So let me know where your confusion is. All right, so let's proceed with the t-test experiment. What do we have? We know, so let's maybe first isolate the math scores. We have our math scores as students math score. We know that we are working with an alpha of 0.05 We know that the hypothesized mean is 70 marks, we are told, and we would like to work with multiple sample sizes, one at a time. So we have 50, 100, and 200. So we have 50, 100, and we have 200. This is known. So now if we have to compute this thing manually, how would we do that? So first let us iterate over the sample size. So we have one. We would like to sample out this number of points. So how do we do that? We can say our sample is max scores dot sample. We take a uniform sample. N is equal to sample size. This here is MPL. This becomes our sample. From this sample, we get our sample mean. We get the sample standard distribution. Now notice that here, because this is not a population, this is a sample, we also pass the degree of freedom. You can again go to the pandas documentation and you can figure out what this DDOF means. Essentially, it is the degree of freedom in this case, because this is a sample, not a full population. So we have our mean, we have a standard deviation, we can compute the standard error, which would be our sample STD divided by the square root of our sample size, which we have. Okay, so we have our basic information. We can also keep note of our degree of freedom, which is essentially the sample size minus one in this case. So once we have these, we have to calculate the t statistic, which is pretty much the same as you do that with the z-test. So the t statistic or the t stat is equal to your sample mean minus your hypothesized mean divided by your standard error. This is your t stat. Now to compare this, because this is an inequality, it could be greater, it could be less than, we have to do a two-sided t-test. We need a t-critical on both sides. We need a t-critical lower and we need a t-critical upper. So how do you compute that? You go for stats dot t distribution as we used to do for normal distribution, and we go for ppf alpha divided by 2, and you provide a degree of freedom df. So you would notice it takes two things in this case. LOC. So you can maybe look at the other. This one is not correct. So in this case, it takes two things. It takes the probability that you want to compute for and the degree of freedom that it should work with. So this is the left side. We would also like the right side, which is 1 minus alpha by 2, and you have this thing. So we have these two. Now we have to make a decision. Based on this t statistic, we will calculate a p-value. Our p-value will be similar to our, as we used to do with the z-stat. We will say 1 minus the stats dot t dot cdf absolute value of my t statistic. And again, we have to pass the degree of freedom as the degree of freedom. This is a two-sided test, so we double the value and then we decide. We say that decision underscore manual is equal to reject my null hypothesis. This is a short form of writing this in two lines. So we can reject if my p-value is less than alpha, else we fail to reject our null hypothesis, and then we can print our decision. We can maybe also print out some extra things. For example, we can print out our t statistic was this much, we can print out that our critical t values for alpha equal to alpha and a degree of freedom equal to this much, whereas follows, where the lower critical value was this and the upper critical value was this. And because we are working with different sample sizes, let us also print that. We can say our sample size was this much, and to add a bit of aesthetics, we can do this. Okay, so for our sample size of 50, we got these values. Wait, let me also add some formatting. Okay, so we got these values. So we get for a sample of 50, we get this. For a sample of 100, we get this. You should also add a new line. 100, we get this. 200, we get this. You would also notice that these values are changing as we run it repeatedly. This happens because we are taking a uniform sample at this point and we have not passed a seed. So what we can do is we can say random seed is equal to 7. And in this case, oh, random state. If you run repeatedly, this value should not change. Okay, so you notice that when your sample size is small, for example, in this case 50, you fail to reject your null hypothesis. You increase your sample size to 100, you still fail to reject it. But at some point, you are able to reject it. So this means that if you have a small sample size and you say that, okay, I'm not sure whether I should go ahead with this, but as you gain more evidence, you can confidently reject your size. So I think you would have noticed that your professor repeatedly said that as your value of n increases, you gain more evidence, and then you can confidently say whether you should or should not reject your null hypotheses. Now, we can do all of this thing using a library as well. So to do that, we once again have to iterate over this thing. That is, we have different sample sizes. In that case, we will create this sample similarly. Okay, we have our sample. To get our t start and our p-value, we can use stats dot t-test single sample here. See, this is the test for the null hypothesis that the expected value is independent observation is equal to the given population mean, or etc. etc. This is for one group of scores. So we can use this particular thing. What does it expect? It expects a sample and it expects your hypothesized mean. So this returns both of these things at once that we have to calculate all of the way here. That is the t statistic and the p-value. We calculate this thing. Let me see if it also takes alternate two-sided. Yeah. So we want it to be two-sided. Okay. So we have this, and then we just have to print this. We can repeat this part. That is that t statistic was this much. Our p-value, where did we not print our p-value? Hmm. So we also print our p-value, and our decision underscore sci-fi is essentially the same thing that we wrote here. You reject If it's less than the alpha, otherwise you fail to reject and then you print. Right. So let's see if we get the same results. We have 7198, 7198, 16531, 16531, 22796, 22796. We fail to reject in the first two methods. We are okay in the other. Any doubts in this thing? Okay, if this is clear, let us move on to proportions. We can close this, close this. Okay, so in this case, we have a telecom company claims that their customer churn is 20%, which means that 20% of their customers have stopped using their service. This is their claim. We want to verify this claim. That is, we believe that actually more than 20% you drop their service. So this essentially is your proportion that Pranay was also speaking about earlier. That is 20% of something they are dropping out. So in this case, given that your null hypothesis is that my churn is 20%, my alternate hypothesis would be that my churn is, we could do maybe just greater than, or we can also do not equal to, we'll see. We have greater than 20%. This is our alternate hypothesis. Can you test whether their claim is correct, given that your alpha is once again 0.05? Let me give you the data. In this case, maybe let's create our own data. Let's say I have this prepared. Okay, so what are we doing in this case? So first we set a seed so that we have reproducible results. We are saying that we need a total of 500 customers for this data. The company, we said that they say that we have 20% turnout, but by design, let's keep it at 25%. That is, we design it so that the company is lying to us. So we create a data frame where we have these customer IDs, and for every customer, it is a binomial that is essentially a coin flip. That is, you either drop out or you remain there, and you drop out with this percentage, 25% drop out, 75% remain there. And based on this, we create this particular data set. If we would like to also look at the data, it looks something like this. Like someone dropped out, remained, someone dropped out, someone remained, something like this. And in this case, you have that notion of P, 1 minus P, and things like that. Okay, so based on this, can you identify, this particular claim of 20%? That is, if I take a particular sample, I get a different value. Is it statistically significant? Do I need to learn Python libraries or anything? So, Tanu, I believe the professor expects that you already know Python, because in the very first week, I don't think he gave any intros about how what is pandas or how to use pandas. I think he believes that is a prerequisite. So yes, if you found it difficult to follow along, that is how what is going on, then I believe you first have to pick that up to cover this side, pandas. Once you cover those, you can anytime revisit these lectures. They are on YouTube. So if you're familiar with Python, pandas should not take you that long, maybe a week or so if you try it daily. Yes, that's the thing. So if you are familiar with Python, then you have to pick up these libraries. You will find ample playlists on YouTube that teach pandas. You can learn it in a week. It's not that big of a deal. Yes, NumPy, pandas, and Matplotlib, these three should be good enough. Yeah, let me in fact give you this data. Sorry. Uh, Block Python. So for the exam questions, I believe there is a separate set of TA. So we are not aware of any of that. So there is a professor. He has one team that works on the exam side, on the theory side. That is, if you have these lectures, if you have any doubts in that, they clear that. There is another set of TAs, which includes me. We cover the practice part and the coding part. So we have no knowledge of what comes in the exams. So I've reiterated it multiple times that there should be a Google group. There used to be a Google group in past sessions, so this time too, I think there should be one. You should maybe contact the coordinator or the professor directly. That is, if there is a group where we can ask these questions, please let us in, give us a link or something, and there you can connect with them. So Tanu, to understand this code, you just need those three libraries as I mentioned. You need the basic of Python, that is, you already know that, assuming, and you need three libraries: NumPy, Pandas, and Matplotlib. That's it. Okay, so maybe we can start with this part with the proportions. So in this case, because there is that formula of P, P, etc., so I prefer to use that terminology of P0 and P alternate rather than writing the full thing in variable. So we'll work that way. We know that our null hypothesis says that the proportion of people who are dropping out, that is P0, is 20%. So we will write that the null hypothesis says that this is 20%. We know that the alternate says that P hat is my sample mean, which is churn data dot, this is churn. You can also write it like this. You can write it like this, churn dot mean. So notice that taking the mean is same as taking the proportion because this is binary. So that's essentially the same thing. So we have the mean. We what do we have? We also have n, that is our sample size. Our sample size is length of our churn data, and these are our given things. So whenever we go for these proportion tests, there is always a check involved. That is my n times p and n times 1 minus p, both of these should be greater or equal to 5. So this is essentially your test for normality. That is the greater than sign. So what happens is, when your binomial distribution, when your n is quite large or your p-values have a certain values, it converges to sort of a binomial distribution that allows you to do these particular tests. If your n is small or your probabilities are very shaky in that sense, like one is quite large, the other is quite small, in that case, it is not a good approximation of this distribution, and therefore you cannot apply this particular test, the t-test or anything that we try to do. For example, in this case, we'll apply the t-test. So that won't be feasible if this assumption does not hold. So let us try this part out. We say if n times my null hypothesis is greater or equal to 5, and n times my 1 minus p0, that is the probability of not flipping. If we take the coin analogy, both of these should be greater than 5, then we can say that print normal assumptions or normality approximation holds. Okay, so both of them are true, we can go ahead. So what do we need? We need the, so the main thing is we want to calculate the z statistic. which is given by p hat minus p0 divided by the standard error. We have p hat, we have p0, we don't have the standard error. So what is the standard error? The standard error is given by the square root of p0 into 1 minus p0 divided by n. So we can write it in a single line. This is the standard error. This is our z statistic. From this z statistic, again, we can compute our p-value. Now it essentially translates to what we have been doing all along. So for the z statistic, we again go to the same thing. We have 1 minus stats dot norm dot cdf. We just supply the z statistic and we can take the decision based on this. We can say reject the null hypothesis if my p-value is less than alpha. Did we define the alpha? We should also define the alpha. So it is the same throughout, so that's okay. Is less than alpha, else fail to reject our null hypothesis. And now we can print these things. We can say that my z statistic came out to be this much. My p-value came out this much. My alpha is known, so what is my decision? Did we miss something? P-value decision. Yeah, so my z statistic is 3.46. My p-value came out to be this much. My alpha is 0.05. We could also print that part. Okay, so we can safely say that we can reject our null hypotheses. Notice that we did not double the p-value because this is a one-sided t-test. We believe that a greater proportion of people are actually dropping out of the service. So how can we do this thing using a library? So this was part one, that is manual computation. Manual calculation. Okay, let's do a library version. So for the library calculation, we will use this particular library called stats model. So this is an alternative for SciPy. So it has a lot of additional tests if you are a statistician, like um, SciPy is good, NumPy is also good, but if you want to go into pure statistics, then this pretty much covers everything, stats models. So we want to use this one, that is proportion z-test. So you would notice that it takes these things. It takes the count, that is how many data points are you working with, number of objects, which is the number of trials or observations. You have your value, which has a certain default values. The alternative in our case would be larger because we believe that more people are dropping out than they have reported. And finally, this is the critical part, which we will see what happens with this thing. So we have to do our, this returns two things. It returns the z-stat, it returns the p-value. So if we say our z-stat comma p-value is given by, we can import this thing. We can say from stats this, import this, and we would like to call this. So the first thing is the count. What do you pass in count? The number of successes in this thing. So we have to essentially sum our column. The number of ones is the number of successes. So we can say churn underscore data churned dot sum. This is the number of successes. This next part is number of observations, which is essentially your sample size. Number of observations, it is equal to n. That is the second part. Then we have our value. Value says this is the value of the null hypothesis. So essentially your 20% that they are reporting. So 0.20, or we can say P0. The next thing is the alternative. We mean we don't have to do a two-sided thing. We are doing a one-sided on the larger side. So that is the final thing. Suppose we run it like this and we keep the default value of this thing, the prop value. Let's see what happens. Then we print all of this. This is Z star, this is P value, this is alpha, and this is decision, 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 decision. This is the decision. If P value is less than alpha, we print this. So notice that the Z statistic is different. In this case, the Z statistic is 0.1528. This is 46. The P value is also different. 0.0003, 0.008. And even though the decision is the same, the output is not the same. This happens because by default, this prop value, it changes this particular calculation, the standard error calculation. In our standard error, we have used the square root of this thing, the product of P0 and 1 minus P0. By default, it does not use this, the null hypothesis P0. It uses something else. So if we want to enforce this particular behavior, we have to pass prop value equal to P0. And now, did we change something? Prop var. Now you would notice that they are identical. 4659, 4659, 0003, 000C. So this part is important. That is, what do you pass here? So based on this, we get identical results. Any questions on this part? Can we find the problem session video recording or not? Yes, you can find the recordings on YouTube. I'll show you the channel in a minute. Any questions on this part? So you'll find the recordings here. So this is the past 3 weeks. You will find this one here. Okay, if proportions are clear, then we can go to the last question, which we could give a homework as well. So this one we will do for the errors, that is the type 1 and type 2 errors. We can close this part. So you are a healthcare analyst investigating whether the average medical cost for smokers is greater than 30,000. You have some patient data and you believe that smokers have to pay more than 30,000 for whatever period that you are noticing. And based on this, you already know that your population sigma is equal to, suppose, 10,000, and you would like to test your hypothesis. Your null hypothesis says that the average is less or equal to 30,000, and your alternate hypothesis says that no, it is actually greater than 30,000 for these smokers. Okay, so this part we know how to do. We have done it thrice now. Okay, we know the sigma, we know this, we know we have to do a z-test, we compute the p-value, or we can do the critical value. Anything works. Okay, what we are interested in is, can we compute the type 1 error rate, can we compute the type 2 error rate? And for the second part, in fact, I would say, can you do it theoretically? Can you do it empirically? So how would you do it theoretically? You would notice that in the lectures, the professor used a function called, I think, type 2, something like that. This thing calculates theoretically your type 2 errors. So this is one way to do it. Empirically, how would you do it? Empirically, essentially, what you're saying is, suppose my hypothesis is this. This means that I am assuming a normal distribution that has mean of mu 0 and a standard deviation of std 0. I have another alternate normal distribution which has a mean of me ma and a standard deviation of std a. Okay. Can you utilize these two values along with this information, that is this alpha, to calculate essentially the overlap between these two distributions? This normal distribution, assuming it's on the left hand side, this normal distribution on the right hand side, the overlap between them on the decision parts, that is essentially your type 2 error. Can you do that? So I would like you to think about this, especially the empirical part. You essentially have to sample out these points. So I would like to give it as a homework question. And as usual, you will find the solution in the notebook later on. If you would like the data, let me paste it here. You can maybe take a screenshot of the question as well if you would like to take a look. Is there a way we can access the notebook? Yes, you can access the notebook. Every YouTube video, if you would notice, below the YouTube video, there is a link that is, you can find the code here. When you follow this link, you get to this GitHub repository, you go into notebooks, and there you will see week 1, week 2, week 3. So today is week 4, you will see another notebook week 4 in a couple of hours. So you can always revisit. For the video, you go here. For the code, you go here. Any questions? Okay, so if there are no questions, I would end the meeting. I'll upload the code on GitHub. You'll find the recording on YouTube. See you all next week. So that theoretically, as I said, you can, I think it's the second last lecture of this week. There will be a function called that type 2 thing. Essentially, it is the overlap between these two functions, these two distributions. The null hypothesis has its own Gaussian distribution. The alternate hypothesis has its Gaussian distribution. The overlapping part essentially between the two, that will give you that error rate. You can refer to that part, or you can also maybe search online. You will find it there. That is type 2 errors in hypothesis testing. There is a way to do it. In any case, I will upload the solution. You can also check it there. All right.